Hello. Can you hear me? Okay, great. How is everyone? Hello Jafar, hello Spawn, hi Manahil. I'm assuming the screen is visible, yes. Yeah, seems to be visible. Okay, perfect. So, do you have any questions or should we begin? Okay. All right, let's do this then. Okay, so in the last lecture we did mathematical induction, right? So we did mathematical induction, and we're going to do two things today. The first is we're going to look at strong induction, and the other thing that we're going to do is the pigeonhole principle. So this, I believe, is still chapter 5.2, and this is, I think, chapter 6.2, which is not to say that there's nothing else in chapter 5. There's recursion, recursive algorithms, there's program correctness in chapter 5, something that I'm not covering. I'm only going to give an overview of strong induction and then move on to chapter 6, and even in chapter 6 it contains lots of ideas, but I'm just going to do the pigeonhole principle with you, right? Okay, and so let's just get into the meat of the issue. And so let me just start by recalling what we did in mathematical induction. So mathematical induction, more specifically what we did for proofs by mathematical induction. So we noted that if you want to do a proof by mathematical induction, then you had to prove two things. You had to prove the base step. So let's suppose you're proving pk for all k greater than perhaps 1 or greater than 0, greater than 2, whatever, greater than some base number, right? And so you prove the base step, which is you show that p of 1 holds, and of course this 1 can be any integer that you're starting from depending on what your statement is. And the next step is to do the inductive step, which is to show, you don't show a statement, you show a conditional statement in the inductive step that you show that pk implies pk plus 1, right? So if pk is true, then pk plus 1 is true, that statement is true. And that's something that we did in mathematical induction. And so now for today we are going to do strong induction, and the idea is essentially the same, except so the base step is exactly the same, that is, we show that P1 holds or whatever you have. But the inductive step is slightly different. In the inductive step, you don't show that the truth of pk implies the truth of pk plus 1. You show that the truth of, so in the assumptions, what you do is you assume p1 and p2 and p3 dot 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 up until pk, and you say that if I assume that the statement holds for all values of k from 1 to k, then it implies that pk plus 1 is true. So let me just write that down in words. In mathematical induction, what we do is we say that assume it holds for k, then show that the truth of k plus 1 follows. In strong induction, what you're doing is you're saying that assume it holds, whatever statement that you're trying to prove, you're saying assume that holds for 1, 2, 3 up until k, and then show that the truth of k plus 1 follows. And if you think about it, these are essentially equivalent statements, because, for example, the strong induction is telling you, so the strong induction is telling you that if, let's say you have k is from 1, 2, 3 dot 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 up until k plus 1 dot dot dot, and you wanted to prove it for all n, right? What strong induction is telling you, in strong induction, what you do is you first prove it for the first statement, base step, and then you say, okay, I want to prove it for k. Let's say assume that it holds, for p1, p2, p3, pk, all of these hold, then the truth of k plus 1 follows. So we show this pink statement that I've drawn visually, we show that this statement holds. Now this is also equivalent to mathematical induction, because let's suppose you have the truth, the assumption is still valid, because let's assume you have the truth for 1, right? So you have the base step, which means the truth of 1 is fine. Now if you want to show that it holds for 2, you already have the inductive step. Inductive step asks you that the truth of statements holds for all previous k's before 2. So it holds for all previous k, right? So if this is k plus 1, then the numbers from 1 to up until k is just this statement. So using the inductive step, it follows that the truth of 2 follows. Now if you want to show it for k equals 3, then you have the inductive step, which assumes that you have proven it for all previous statements, you've proven it for 1, you've proven it for 2, then you can combine these two and use the inductive step to assert that the truth of 3 also holds. And when you move up for 4, then of course you have the previous 3 statements to rely on and you can prove. What was different in in simple induction, so something that we call weak induction, is that when you were going from 1 to 2 and 2 to 3 and 3 to 4, then for 2 the inductive step only needed the assumption for 1. For 3, the inductive step only needed the assumption for 2. We did not need the assumption for 1, even though it's still there if you want it, right? Does that make sense? In sum of odd numbers example, you use the same method. You're talking about the assignment problem that I posted? Yes, we do use induction in that. Is that what you're talking about? Anyway, let me know if this is clear. If this is clear, we can do an example and then move on to the pigeonhole principle in lecture. In the previous lecture? So in the previous lecture, we were only assuming the truth for the previous statement, not all the previous statements, right? There's a slight difference in the inductive step. The inductive step for mathematical induction only assumes pk implies pk plus 1. The inductive step for strong induction assumes that they should be all true from 1 to k to prove k plus 1, right? There's a slight difference. I don't think the example that I did for sum of odd numbers, I used strong induction, I used weak induction in that. So you may go back and see that we must have proved pk implies pk plus 1, right? But that's weak induction. Okay, great. So let's do an example. Let me pull that up. Okay, so here's the example. Show that if n is an integer, if n is an integer greater than 1, then n can be written as the product of primes. Then n can be written as the product of primes. Okay. All right, so let's do this. And so the proof is done by strong induction. So we want to prove the statement for n greater than 1, which is basically n is greater than or equals to 2. We want to prove that the statement holds for n greater than or equals to 2. Okay, and so we know what primes are. Primes are 2, 3, 5, 7, not 9, 10, 11, 13, and so on. Okay, these are primes. Also, just by the way, if it's a prime, for example, if it's 2, then 2 can be written as 2 times 1, 3 can be written as 3 times 1. And this is a valid product of primes because 1 is neither a prime number nor a composite number. It's called something which is an empty product of primes. So this is still valid, right? So it can be written as a product of primes, which is it's the prime 3 times itself. So it can be written as a product of primes. So if it's prime, the statement holds, right? And so let's go ahead and prove this. So the idea is we first use the base step, so we're proving by induction. So proof by induction, which is the first, so the first base step, the base step has to be the first positive integer that we're considering, which is 2. So we know we need to show that the statement holds for true, so that 2 can be written as the product, as a product of primes, and we know that 2 is a prime number itself, so we don't even need to check it as a product of primes, and of course it's true. You can just write it as 2 times 1, or you just write it as 2, right? So 2 can be written as just 2, right? And that's fine. The second step, which is the inductive step, and here we're going to use the principle of strong induction. So we want to prove, we assume that 1, 2, 3, or rather from 2, but so on, let's exclude 1. So 2, 3, 4, 5 up until k can be written as a product of primes, and then we show that k plus 1 can be written as a product of primes. So as a product of primes. Now let's say k plus 1 is some number, right? So k plus 1, my assertion is that k plus 1 can be written as a product of primes. So p1, p2, p3, so on, right? Okay, and so there are two possibilities to consider. The first one is k plus 1 is prime. So I'm doing a proof by cases now. So k plus 1 is either prime or k plus 1 is not prime. If k plus 1 is prime in the first case, if k plus 1 is prime, then k plus 1 can just be written as k plus 1, where this is a product of primes, right? It doesn't need anything else, it doesn't need any other prime, and we can clearly assert that the statement holds if k plus 1 is prime. So in the case when this is a prime number, so for example in the list of these numbers, if you had a prime number, there's 3, 5 and so on, this is valid, so we don't need to care about that. Okay. The second case is when k plus 1 is not prime. If k plus 1 is not prime, then it means that it is a composite number, which means k plus 1 can be written as a times b, right? So it can be written as the product of two numbers, where a and b are both positive integers. That's the first thing. And of course, if k plus 1 is being written as the product of these two numbers and they are both integers, then I can assert that both of these numbers are going to be bigger than 0. So bigger than 0, and they may be equal as well, but they're definitely going to be smaller than k plus 1. Okay, so on the line of integers, when we have k plus 1 here, if k plus 1 is a composite number, then a must be somewhere here and b must be somewhere here, but of course greater than 0, because this is a, they are both positive numbers. Okay, and now we have two numbers which are smaller than k plus 1, but for numbers that are smaller than k plus 1, integers, we already know that it holds. So we know that a can be written, because that's the inductive assumption that we've made, can be written as a product of primes. And we've also assumed that b can be written, because it's a smaller number than k plus 1, so can be written as a product of primes, which means this is just a product, right? So k plus 1 is just a product, so it's a product of primes as well, because both these numbers are products of primes. So what if this is p1, p2, blah blah blah, and if up till pn, and if this is pn plus 1, pn plus 2 up until pn, then when you multiply these, k plus 1 can be written as p1 dot 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 pm. So k plus 1 therefore is a product of primes. And so even in the second case, when you have a composite number, the truth of k plus 1 follows. So I have shown that if I assume that it holds for all these statements up until k, then I have shown that it holds. So I have proven the inductive step as well, and I have already proven the base step. So the proof is therefore complete. Therefore any positive integer can be written, and we can check this, of course. So let's say if we have the list of n's, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, then for the primes it's valid because primes can just be themselves and they don't need to be written as a product of any other prime. So 5, it holds for 7 and 11 and so on. And for the remaining numbers which are composite numbers, so for example if 4 is a composite number, then 4 can be written as 2 times 2, and of course this is just a product of primes. 8 can be written as 4 times 2, and of course I've already proven that 4 can be written as a product of primes, so we're done. And you can see that this follows for all integers. If you assume it for k, then the truth of k plus 1 follows. Okay. Yes. So when you're thinking about products, Jafar, you don't even need one. For example, when we're writing prime factorizations, if you recall, when we're writing prime factorizations, we write 6 as 2 times 3. We don't write 1 over here, right? So product of primes doesn't contain 1. Even if we did include it, it doesn't matter, because 1 times any number is just that same number, so 1 doesn't matter. So similarly, if for example you have 9, then 9 is simply 3 squared. If you have 10, then that's 2 times 5. If you have 12, that's 2 squared times 3. So these are all product of primes. So similarly, 3 is just 3, 2 is just 2, right? You don't need anything else. 11 is just 11, the product of primes. Yeah. Okay, so is that clear? If that is clear, then we can just move on to the pigeonhole principle. Okay. All right, let's move on. Okay, so now we have the okay, so the pigeonhole principle. Okay, and this principle is going to sound very trivial. It's actually very intuitive. There is actually, once I write it, you're going to ask me and you're going to wonder why are we writing down such a trivial statement, but it has its uses, right? And it's very useful in proving some statements. Okay, so here's the statement of the pigeonhole principle. If k is a positive integer, if k is a positive integer and k plus 1 or more objects are placed into k boxes, then there is at least one box containing 2 or more objects, which is basically saying that if you had let's say you had box 1, box 2, box 3, box 4, until k boxes. This is box number 1, box number 2, box number 3, up until box number k. And it's saying that if you had k plus 1 object, so object 1, object 2, object 3 dot 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 up until object k plus 1. If you wanted to place these objects in these boxes, let's say object 1 went here, object 2 went here, object 3 went here, and so on. Or maybe you can put in two or more objects in one box, and the statement is if you want to fit all of these objects in these boxes, then one of them has to contain two or more objects. And that's pretty obvious, right? Because if you want to avoid adding two or more objects in these boxes, then you're fine up until object k, because then you can place all of them in different boxes, right? So all of them will be in different boxes, but as soon as you reach the k plus 1 object, you have no other choice but to put it in a box which already contains an object. So once you've reached the same number of objects as boxes, the next object has to be placed in a box that already contains one. So k plus 1 or more objects are placed into k boxes, then this statement holds. Is that clear? Yeah. Okay, and so let's do an example here. So in other words, इसको प्रिंसिपल किसने बनाया? ये Dirichlet, however you want to pronounce it, Dirichlet, KNN, I have no idea who that is. But yeah, so here's a statement. So there's a corollary of this principle, which is a function from a set of k plus 1 objects, or k plus 1 elements, k plus 1 or more elements, to a set of k elements cannot be 1 to 1, right? And that's the same thing being said in a different ways, which is that if you're mapping a function from set A to set B, so this is set A, set B, if set B contains k elements, so B1, B2 up until Bk, and if you have set A which contains A1, A2 up until ak plus 1, or perhaps even more objects, but at least k plus 1 objects, then these objects, then this mapping, if you want to create a map from A to B, if you want to create a function, then you can't create a one-to-one function. So you can make A1 to B1, A2 to B2 up until ak to bk, but by the time you reach object ak, all of the images in the all of the elements in the codomain B have been used up. So ak plus 1 must be mapped onto some object, some element that has already been mapped by some previous element, right? Is that clear? जी जाफर, आप थोड़ा गलत सेंचुरी में पैदा हो गए. अगर आप पहले पैदा हुए होते तो आप भी मैथमेटिशियन फेमस हो जाते. Okay. Alright, so here's a question then. Let's suppose, question, or rather among is a statement, right? So example one, among a group of 367 people, at least two share the same birthday, right? And this is simple. This is just the application of the pigeonhole principle, because if you think about the people as objects, so people P1 to blah 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 P367, and you have dates available to you, which is you have about a total of 365 dates, right? In a year there are 365 days, so the total boxes that you have are 365. So this is people and these are birthdays, right? And so if person 1 was born on 1st January, person 2 was born on 2nd January, person 365, person so we're accounting for leap years as well, right? So let's say 29th February is there as well, so 366, right? Is, yeah, so 366. And so if person 366 was born on 31st December, then the 367th person will have to share a birthday with someone else, right? Okay, let's do a problem. Here's a problem. Question: how many students must be in a class to guarantee that at least 2 of them get the same score in the exam if the exam is graded in integers from 0 to 100, right? That's the problem. And I'll give you a few minutes or perhaps 1 minute to think of the answer for this. Yes, Jafar, it's not asking about how many you can fit in one birthday. It's asking for at least 2 people. So the keyword here and in the pigeonhole principle is at least. So at least means greater than equals to 2. So 5 is greater than equals to 2, and that's completely fine. This is turning into statistics. Sure. Okay, and so from 0 to 100 there are, Jafar, you're absolutely right, from 0 to 100 there are 101 possible scores. So if these are the boxes, then if you have 102 students, then they are guaranteed to have 2 or more students will get the same grade, the same score, right? And this should seem trivial. Okay, all right, let's do another problem which is not so intuitive. Show that for every integer n, there is a multiple of n that has only zeros and ones in its decimal expansion. So what is this statement asking you to prove? It's asking you to prove that, let's say n is some integer, right? So n is equals to 5. Then there is some integer of 5, then there is some multiple of 5, for example m times n, such that it can be written with only ones and zeros. And of course for 5 it's simple, you know that 2 times 5 is equals to 10, and it only contains 1 and a 0. You can think about some other number as well. Let's try to do it for 7. So n equals to 7, we are asserting that there exists some m times n, which can be expressed as 1, 0, 1, 1 something, right? And we are saying that it's true for all possible integers. Now, how do you prove this? Right? Okay. And so this, at first glance, this doesn't seem like an easy problem, because we are asserting that for every integer, some m times n can be written as 1, 0, 1, 1, 0, blah, blah, blah. And we don't even know which integer, we don't even know how many decimal points we have, how many, what's the size of this, what's the order of this multiple, so we don't know how to do this, right? And so how do we prove this? अच्छा सिंपल ही है, तो आप प्रूव कर दें, बताइए कैसे होगा? Without looking at the book. Okay, and so here's the proof, and we prove it by the pigeonhole principle. So here's the proof. Consider the integers 1, 1, 1, 1, 1, 1, up until, so this was the first integer, this was the second, third, and we are going to consider n such integers such that the nth integer is 1, 1, 1, 1. So it has n ones. Okay, these are the integers. Any confusion so far? Okay, at this point I am going to bring in modulo arithmetic, and ask you to consider the remainders. What are the remainders? What are the remainders when some number is divided by n? What are the possible remainders when you divide any number by an integer n? So basically I'm asking you the equivalence classes in Zn. What are the equivalence classes in Zn? What possible integers can you have? Yep, so the possible integers that you can have is 0, 1, 2, dot, 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 n minus 1. So every possible number has to be from one of these equivalence classes, right? So if you want to find p mod n, then it's going to come from one of these equivalence classes. So far so good? Any confusion? Okay, and now here's the thing. So from 1 to n, these are I need, so we have from 1 to n, from 1, 1, 1, 1, 1, 1, and so on up until this nth. I think I'll need one more. So let me add one more to this list, 1, 1, dot, 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 1, with n plus 1 ones, right? So I have n plus 1 integers. If I convert all of them in modulo arithmetic, so 1 mod n is of course simply 1. 11 mod n has to be some number between 0 to n minus 1, right? Congruent. in one of these classes, 111 mod n also is going to be one of these boxes. So if I have n plus 1 integers, I have n plus 1 integers, and the possible remainders that I have, are n possible remainders, right? So then one of them, at least two of them, by the pigeonhole principle, at least two of them will have the same remainder. Do you agree with that statement? There are n plus 1 integers, and the possible remainders that we have are just n. Does it make sense? Okay, here's the list. The boxes, the numbers that I'm dividing, we're dividing 1, 1, 1, 1, 1, 1, and so on up until the number which has n plus 1 ones. I'm dividing all of these numbers by n. So the number of numbers that are being divided are n plus 1s, and the possible remainders, when I'm dividing by n, then of course the possible remainders will be 0, 1, 2 up until n minus 1. So how many numbers are these? These are n remainders. So if you start counting from 1 to n minus 1, you have n minus 1 plus another 0, which gives you n remainders, and these are n plus 1, and these are n plus 1. So when you divide these by n, the possible remainders that you get are going to be n, right? So let's say 1 has remainder 1. So 1 has remainder 1, 11 has some other remainder, 101 has some other remainder. Then if I'm going to pick n plus 1 objects, n plus 1 numbers, and divide them by the same number, then two of them at least by the, because if you think of these as objects and think of these as boxes, then you have to place n plus 1 objects in n boxes. Does that make sense? Excellent. And at this point I will bring up another fact. So let's say now I know that there exists A and B. Let's call this, I'm going to call this list L. There exists A and B from list L such that A is congruent to B mod n. Does that make sense? B mod n is nothing but the remainder when it is divided by n. So A and B are congruent to each other. There are two such numbers in this list. Okay? And now from the definition, if you recall the definition of modulo arithmetic or mod n, this implies that if A is congruent to B mod n, then that simply means n divides B minus A. Okay? So n divides B minus A, which means that B minus A is a multiple is a multiple of n, which is that b minus a can be written as sum m times n. Is that clear? Jafar, L is the list of the numbers that are being, not the remainders list, but the numbers that are being divided. So this list 1, 11, 111 and so on, 1111, all of these numbers. Okay, is this clear? If you don't recall this, then let me jog your memory. For example, if you divide 7 by 3, the remainder is 1. If you divide 4 by 3, the remainder is 1. That means 7 is congruent to 4 mod 3. And if you subtract 7 minus 4, you get a multiple of 3. And you could have done that by 10 as well. If you divide 10 by 3, then the remainder is still 1. And so 10 is congruent to 4 mod 3. And if you subtract these two numbers, 10 minus 4, then 10 minus 4 gives you what? 10 minus 4 gives you 6, which is of course a multiple of 3, which is to say that a minus b, if two numbers are congruent to each other mod n, then if you subtract the smaller number from the bigger number, then you're going to get a multiple of the integer that you're doing modulo arithmetic in. Okay, and so here's the idea. The number that we needed, the required multiple of n is b minus a. And I'm going to state something which I'm not going to prove, and you're going to think about this. B minus a contains only ones and zeros in its decimal expansion. Let me know if that's clear. Why am I saying b minus a contains only ones and zeros in its decimal expansion? Because b and a are both coming from that list. So b is perhaps 1 1 1 1 1 1, a is some 1 1 1 1, and if you subtract these two numbers, then you're only going to get ones and zeros, right? So if this one had 1, this was going to have 1 1 1 1 0 0 0, and so on. And that's the number that you're looking for. This is just an example. This is not the specific number, but you will only get ones and zeros in the expansion. No, it's not remainder that's going to be 0 and 1, Jafar. When you subtract them, the digits are going to be 0 or 1. We're done with the remainders. The remainders were only there to prove that some of them will have the same remainder, and then you can write them as a multiple of n. Okay. So b minus a is that multiple m times n, which contains only ones and zeros, and that finishes your proof. Okay, any confusion? No? Great. So how about let's go one step further and let's do the generalized pigeonhole principle. And let's do it with an example. Suppose there are 21 objects. Then if they are placed in 10 boxes, then one of them will contain 3 or more objects. Does this statement make sense? It's saying that if I have 10 boxes, 1, 2, 3, box 1, box 2, box 3, dot dot dot, box 10. And if I have to place 21 objects in it, then it's going to contain, at least one of them will contain 3 or more objects. And it's easy to see why. It's easy to see because let's start putting objects in these boxes. So objects 1 to 10 can be placed like first object here, another object here, another object here, and 10 objects have been placed in 10 boxes, right? Let's say I'm trying to avoid putting 3 objects in one box. Then objects 11 to 20 can be placed by placing the next object here, another object in this box, another object in this box, another object in this box, right? And so now when I reach 20 objects, each box contains at least, not at least 2, but yeah, at least 2, because I'm trying to put them in separate, but now they contain exactly 2, right? And I was trying to avoid putting 3 objects in one box, right? So I didn't put any of them in the same box. And now when I reach object 21, I have no other choice but to put it in a box that contains at least 2. And once I put it in some box, let's say if I put it in box 3, then box 3 will contain 3 objects, right? One of them will contain 12 objects. No, that's not necessary. You can make them contain 12 objects, but it's not necessary that they contain 12 objects. Okay, so the generalized pigeonhole principle says the following: if n objects are placed, so this is the generalized pigeonhole principle. If n objects are placed in k boxes, then there is at least one box that contains n upon k, the ceiling of n upon k objects, right? And so if I use this principle in the statement above, I had n equals to 21 and I had k equals to 10, and so 21 upon 10 was something like 2.1, well, exactly 2.1. Then the ceiling of that number is 3. So at least one box will contain 3 or more objects, right? Okay, and so let's do an example. Do you want me to prove the statement, or do you want to look at the proof yourself, or perhaps you want to even prove it yourself? You can prove it, by the way, you can prove it by proof by contrapositive. So you can prove by contrapositive. I think you should try the proof on your own before you look at it in the book. I'm not going to prove it, okay? I'm just going to do an example with you, and then we're going to move on. Okay, so what is question? What is the minimum number of students in a discrete math class such that to be sure that at least six will receive the same grade, if there are 5 possible grades. And so these 5 possible grades are A, B, C, D, and F, right? And so how many students do you need to guarantee that 6 of them will receive the same grade? And so the simple way to do this is to do the following. The way we do this is to do okay, and so we need by the pigeonhole principle, by the generalized pigeonhole principle, we need R. So 6 of them receive the same grade, right? And so we need 6 to be equals to n upon 5. I don't know how many students there are, but I know how many grades there are, and I know how many students I want to have the same grade, right? And the easy way to do this, one of the ways to do this, of course, is to do n equals to 5 times r plus 1 to solve this equation. And you can think of this in a way that you're talking about you had n students and you want n upon k. So let's say n upon k is going to be some number here, and what you want and what you're looking for is the ceiling of n upon k, which is going to be, if this is some decimal expansion, if this is between some integers, r minus 1 and r, then you're looking for this integer, right? Such that you're looking for an n such that we're looking for an n such that n upon 5, and the ceiling of that number, that is n upon 5 ceil, is equals to, so r was 6, so I want this number. I am looking for such an r. And of course this r, if you think about it, if I multiply r minus 1, with n, then if I multiply r minus 1 with n, with k, sorry, not with n, with k. So if this was divided by 5, then divided by 4 would be somewhere over here. So multiplied by k plus 1. And I think I'm overly confusing the issue, so let's approach it from a different way. Let's approach it from this possible way. Let's think about these 5 grades as grades A, grades B, C, D, and F, right? And let's suppose I want 6 students to get the same grade. And so let's start putting in students in these boxes. So let's suppose I start off by putting 1 in each of them, right? I have successfully managed to place 1 student in each box, and so I now have 5 students, and none of them, but I still don't have 6 students getting the same grade. Let's say I put another one in each of these grades. So now 2 students have the same grade and I have reached 10 students. Okay, let's place another one, 3 3 3. Okay, so I can go up until 5 times 5, right? I can put 5 students in each of these grades and still get no 6 students getting the same grade. And now if I want to go to 26 students, since up until 25 students they can all be equally divided and no 6 of them get the same grade, once I reach the 26th student, as soon as I reach the 26th student, I will have to give them an A, a B, C, D or F, but all of them already has 5 students getting that grade. So if I give them a B, then there are 6 students with a B, and so the minimum number I need at least 26 students. And to do this in the way that I was previously doing by this mathematics was to do 20, so n is basically 5 times 5 plus 1. So this was I was looking for r minus 1, which was, I was looking for an n such that 5 times r was equals to 6, 5 times 6 minus 1 plus 1. Okay, so the way to find this answer is to say n is equals to k times r minus 1. My k was 5 grades, k is the number of boxes, r is the number of students with same grade. I wanted 6 students to have the same grade, so k times r minus 1 plus 1, which is 5 grades, 6 minus 1 plus 1, 5 times 5 plus 1 equals to 26 students. Okay. Let me know if that is clear. Let me know if you want me to do another example. If you don't want me to do another example, we can call this a day and let it be. Clear? Should I do another example? नहीं, फिर बाद में आप खुद ही कर लीजिएगा. Okay, so that is it for today. All right, any questions? Question 6, I will make a video and post it so that you can see it. Just like I did for question 4. All right, that's it. Have a good day. No worries. Have a good time. Bye.